In this video, we are going to examine acid-base properties of common classes of organic compounds. Typical organic acids are carboxylic acids, and while there are other organic compounds that are acidic, these are considered to be typical organic acids. Carboxylic acids are weak acids, and the most common carboxylic acid is acetic acid, shown here. So in aqueous solution, it is dissociated into acetate anion and hydronium ion. Compared to inorganic acids, strong inorganic acids, these acids are very weak, and in aqueous solution, extent of dissociation is relatively low. It depends on concentration, but frequently it's just 1 or 2%. So relatively weak acids, but compared to other organic compounds, they are much more acidic than most other organic compounds. Carboxylic acids are characterized by carboxyl group, shown here, COOH, and so it is this hydrogen attached to oxygen that is acidic hydrogen and that can be donated in the course of acid-base reaction. Two typical carboxylic acids are formic acid with pKa of 3.75 and acetic with pKa of 4.76. And acetic acid in terms of pKa is more typical. Formic is a bit stronger. So typical pKa of a carboxylic acid is between 4.5 and 5. So carboxylic acids, shown here on example of acetic acid, readily react with bases such as hydroxide to be deprotonated, and then with bases, of course, equilibrium is to the right. Reaction goes to completion. But being relatively weak acids, carboxylic acids could actually be protonated by strong inorganic acids. So in the final reaction on this page, you can see protonation of acetic acid to give oxonium ion, and pKa of this oxonium ion is minus 6.1. So any inorganic acid that has pKa larger than minus 6.1 will be able to protonate acetic acid, and equilibrium will be to the right towards protonated acetic acid. Protonated organic cations are actually usually rather strong acids, and here are typical protonated organic cations: oxonium ion, sulfonium, ammonium ion. Their strength varies, but in general they are relatively strong acids. Ammonium may be not that strong, but oxonium is certainly rather strong. But they are, as being ions, they are usually unstable, transient species. So usually they are reaction intermediates. Or also they may play a role of catalyst. So a lot of organic reactions are catalyzed by these acids. So obviously these are very good proton donors, and these are often acids in organic reactions, in longer mechanisms. And here is one example where oxonium ion generated from an ether, from diethyl ether, protonates amine, methylamine. So products are diethyl ether and methylammonium cation. And here are some additional examples of oxonium ions. Hydronium ion is a specific oxonium ion, H3O, so that's oxonium ion that has its own name. The other oxonium ions, all you can see is that they have oxygen that has valence of 3 and positive charge. And that's actually the definition of an onium ion in general. So we have oxonium, sulfonium, ammonium, phosphonium ion. That's ion where central atom has valence 1 higher than usual valence. So usual valence of oxygen would be 2, sulfur 2, nitrogen 3. So 1 higher valence in case of oxygen 3, and positive charge on oxygen atom. So that makes it onium ion. And note the last ion, acylium ion. That ion will be very important in the second semester when we study reaction mechanisms. Yet another type of organic acids are carbocations. We usually don't look at them as acids, but they actually are acids. They have acidic properties because they are good proton donors. So one of the reactions of carbocations is donation of a proton to form an alkene, or in general unsaturated compound, as conjugate base. And that's shown here. So hydroxide anion will abstract neighboring proton from a carbocation, neighboring proton from the neighboring carbon, to give conjugate base or an alkene. Just like previous compounds, onium ions, carbocations are unstable compounds, unstable species, so they are short-lived reaction intermediates. The reason behind acidic properties of carbocations is that electron-deficient carbon is an electron-withdrawing group, and that makes proton on the neighboring carbon acidic. That proton can easily leave as a proton, and electron pair will flow to form carbon-carbon pi bond. While typical organic acids are carboxylic acids, typical organic bases are amines. So amines as a class of compounds are the most commonly used bases in organic chemistry, and if we think about organic base, we think about amines. One example is methylamine. Of course, it does have hydrogens or protons attached to nitrogen, so it could act as acid, but you can see that its pKa is 40. So it really doesn't have any acidic properties. It typically acts as a base, and free electron pair on nitrogen accepts a proton. So in a typical reaction, amine cannot be deprotonated, so it's shown in the first equation. Reaction of amine with a hydroxide does not work very well, so extent of the reaction is very low, almost negligible, and equilibrium is to the left. To deprotonate amine, we would need some exceptionally strong base. On the other hand, second reaction in the second row, reaction with an acid works very well, and equilibrium is completely to the right. So proton donor readily protonates amine to give ammonium cation, conjugate acid. So amines are bases, and their conjugate acids are ammonium cations. We have seen already ammonium cations under acids. Another class of organic bases are ethers. And ethers actually are frequently used as a base. We don't consider ether as a typical organic base, but actually it is. It is readily protonated to give conjugate acid oxonium ion, which we covered earlier. And ethers are very important because they are common organic solvents. And frequently, when they are used as a solvent in a reaction, if they participate in a reaction, they participate as a base. Sometimes solvent is used simply to dissolve reactants so that there is a medium for reactants to encounter and react. But in other cases, solvent plays a role in reaction mechanism. And if a solvent does play a role in reaction mechanism, solvents such as ether usually acts as a base. So one of the two free electron pairs on oxygen accepts a proton to give oxonium ion. Another class of organic bases, which we often don't think of as bases, we look at their reaction mechanisms a little bit differently, but they are bases because they are proton acceptors, are alkenes. So alkenes are readily protonated by acids to give conjugate acids, carbocations. And again, we covered conjugate acids a few minutes earlier. So conjugate acid, carbocation is organic acid. So in this case, starting base, and alkene is actually a base. So pi electron pair serves as a proton acceptor. Proton is donated to the pi electron pair to form new carbon-hydrogen bond and give rise to conjugate acid carbocation. Carbocations have short lifespan, they are reaction intermediates, so they will right away react in the next step to give a more stable species. And then we have numerous classes of organic compounds that can act as both acids and bases in organic reaction. We'll cover only two common classes as examples. One are alcohols. So alcohols, as you have learned earlier in this course, could be viewed to be derivatives of water. And so, just like water, alcohols are amphiprotic. Amphiprotic means that they can readily react as proton donors or as proton acceptors, depending on circumstances, depending on what they react with. So two typical alcohols are two smallest alcohols, methanol and ethanol. And so methanol has pKa of 15.5, ethanol of 15.9. pKa of water is 15.7. So you can see that their pKa is just about that of water. And so just like water, they readily react with bases in the first equation. So with a base such as hydroxide, alcohol is deprotonated to give corresponding alkoxide. And also they are readily protonated by acids. So an alcohol reacts with an acid to give oxonium ion. And this oxonium ion, resulting oxonium ion conjugate acid, is actually rather strong acid. pK is minus 2.5. Another class of organic compounds that can act as both acids and bases are carbonyl compounds. But they are rather different from alcohols. They have carbonyl group, which is carbon-oxygen double bond. But as you can see, that oxygen does not have a proton, which means that different parts of the molecule act as acid and as a base. So oxygen has free electron pairs. So that's basic part of the molecule. Free electron pair from oxygen can form bond to a proton, so the oxygen acts as a base to give corresponding oxonium ion. We have already seen that oxonium ions are acids, so in this case oxonium ion is conjugate acid of the starting carbonyl compound. Now, to act as an acid, carbonyl compound must have neighboring carbon with a proton, and so proton on the neighboring carbon, on the carbon next to the carbonyl group, is acidic proton. And the reason for it is that carbonyl group is an electron withdrawing group. In the next video, we will see why electron withdrawing groups increase the strength of an acid. So ordinary alkane is not acidic. It does not have any acidic properties and cannot be deprotonated simply because CH bond is not polar enough for hydrogen to be removed as a proton. But neighboring electron withdrawing group will polarize that bond, and hydrogen, what we call alpha hydrogen, neighboring hydrogen, hydrogen on the neighboring carbon, is acidic and can be removed by a strong base. So that's the acidic site of the molecule, acidic site of the carbonyl compound. And so here is an example. Carbonyl compound acetone, common carbonyl compound, reacted to base to give conjugate base, inlet anion, and water as conjugate acid of hydroxide anion. This is a reaction that we'll be covering a lot in the second semester in Organic 2 course. This completes our review of acid-base properties of organic compounds, and next we are going to examine acid strength of various organic compounds.